So what do a thrown basketball, a giant suspension bridge, and even the profits of a business all have in common? It might sound like a riddle, but they can all be described by one surprisingly beautiful piece of mathematics. It's called the quadratic equation, and it is the key to unlocking the code of curves.
You see this shape everywhere, this perfect, graceful arc. It's called a parabola. It shows up in the real world constantly, from the path of a water fountain to the shape of a satellite dish. And it turns out there's a very specific mathematical code that governs this exact shape.
So how do you actually write the instructions for a curve? Well, in the language of mathematics, we use equations.
And this is it, the quadratic equation. See that x squared term? That's the secret sauce. It's what literally puts the curve into the curve. And those letters, A, B, and C, they're just numbers that act like dials you can turn to change the shape, the width, and the position of our parabola. Just think about that for a second. By changing only 3 little numbers, this one single form can describe an infinite number of parabolas. It's an unbelievably powerful and efficient blueprint for a fundamental shape of our universe.
Okay, so if the equation is the blueprint, how do we actually use it? How do we find specific points on that curve, like say where the basketball goes through the hoop or where a rocket lands? For that, we're going to need a special tool.
And here it is, in all its glory, the quadratic formula. Now, I know, it might look a little intense, but it's a masterpiece of efficiency. You just take your A, B, and C from any quadratic equation, you plug them in, and boom, it spits out the answer for x. Every single time. It's like a universal key.
And get this thing isn't new. The journey to this exact formula took centuries, with brilliant minds from Babylonian, Greek, and Persian mathematics all adding pieces to the puzzle. But this final, works for everything version has been a cornerstone of math for over 400 years.
But we're not just here to admire the formula. We're here to unlock its secrets. And the most powerful secret of all is hidden in one small part of it, right in plain sight.
Okay, I want you to zero in on just that one piece under the square root sign, b squared minus 4ac. This isn't just some random calculation you have to do along the way. No, this little expression, it's a kind of oracle. It can predict the future of the equation before you even finish solving it.
This part of the formula is so important that it actually has its own name, the discriminant. And its job is literally to discriminate between the different kinds of answers you can get. Just by calculating this one little value, you know exactly what the graph of your parabola is going to do.
All right, let's see how it works. Case 1. If the discriminant is a positive number, anything greater than 0, the formula guarantees 2 different real answers. And what does that look like? It means our parabola is going to swoop down and cross that horizontal x-axis in 2 separate places.
Now for case 2. What if the discriminant isn't positive? What if it's exactly 0? Well, then you get just one real solution. And this is where the math and the picture line up perfectly. That single solution is the exact bottom or vertex of the parabola, just kissing the x-axis at one single point.
And that brings us to the final case. What if the discriminant is negative? Well, you can't take the square root of a negative number in the real world, right? The formula tells us there are no real solutions. And what does the parabola do? It floats. It never touches the x-axis at all. The discriminant knew it the whole time.
So we've got this incredible predictive tool. But does any of this matter outside of a math classroom?
This is the big question, right? Why should you care? Well, the answer is that this equation isn't just some abstract idea. It's written into the fundamental laws of our physical universe.
Seriously, this isn't just theory. This is used to calculate the path of a rocket. It's in the elegant curves of suspension bridges. Economists use it to model profit. It helps determine the stopping distance of your car. It's even used to design the circuits inside your phone. And unbelievably, it shows up in Schrödinger's equation, which is fundamental to quantum mechanics. And here's the absolute crucial link: the relationship between time, speed, and distance when something is accelerating. You know, a basic law of physics is a quadratic equation. That's why it's so powerful. It's not just describing a shape, it's describing how things move and change over time.
For centuries, though, that third case, the negative discriminant, was this really frustrating dead end. But of course, math never, ever stops evolving.
I mean, try to imagine you're a mathematician back in the 16th century. You have this incredible formula that works almost all the time, but then, every so often, it just hits a wall and tells you some problems simply have no solution.
It was a huge puzzle that needed a completely new kind of number to solve it.
And here's that breakthrough: complex numbers. By basically inventing a new number, the imaginary unit I, and defining it as the square root of -1, mathematicians blew open a whole new dimension of possibilities. With complex numbers, there are no more dead ends. That floating parabola from before? It turns out it does have roots. They're just not on the number line we can see. They exist in the complex plane.
This really puts the incredible history into perspective. The quest to solve these equations started with ancient Babylonians literally drawing shapes in clay tablets, and it has led directly to modern software on our phones that can solve ridiculously complicated versions of the same problem in an instant.
And this journey is not over, not by a long shot. A research paper slated for 2025 details a brand new, faster way to solve these equations when things get really complex. So this isn't just history, it's a living, breathing field of mathematics that's still on the cutting edge of discovery.
So we're left with this amazing question. How can something so ancient, a puzzle that was being worked on by the Babylonians, also be the very language we use to describe the flight of a baseball, the motion of planets, and even the bizarre behavior of the quantum world? It's just a stunning testament to the timeless power of math to unlock the hidden codes of our universe.